Good afternoon. Just looking at what we have regarding functions and going back to, let's say, section 1.3 and looking at whether we have a relation to be a function or not. And again, with functions, okay, for each x value, there will be one and only one corresponding y value at most. And okay, now, and among the items, okay, we've have going back to vertical line tests, and we have for the graph in number 16, it says to determine if the relation defines y as a function of x. And so here we have a curve that's in the shape of something about like a W. And if I were to run a vertical line through this, let's say just from end to end, if you notice for each of the x values, okay, you have intersection at most 1 point. Okay, so for what we have in the case of number 16, okay, that one is a function. Now for what we have in the case of number 17, okay, so you have kind of an S-shaped graph and looking at whether we have a function or not. Okay, so just moving along. Okay, so we have a vertical line. So right now we have intersection, let's say to in this region to the left of the y-axis, you have the intersection by at most 1 point. But once we get into the middle section, once we get right at the y-axis, okay, you have like for the same x value, you have intersection between the vertical line and the graph, okay, at more than just 1 point. Okay, so 17, okay, this is a case of a non-function. Okay, so 17 does not pass the vertical line test. Now, in terms of whether a horizontal line can be a function, okay, so if I were to move from end to end, you have intersection at most 1 point. Okay, so a horizontal line is a function. And looking at what we have in the case of a vertical line, okay, and in determining whether that is a function or not, and what's going to happen here is that you're going to have intersection at an infinite number of points. And so in this particular case, all right, you have the answer is going to be no. And in fact, you have intersection at an infinite number of points. So you have like at x is equal to 2. So you have like 2 negative infinity for y. All the way out to 2 positive infinity. So you have not just more than 1 point, but you have intersection at an infinite number of points. So a vertical line cannot be a function. Okay, now for what we have in the case of item 22, okay, and looking at whether we have these line segments, okay, to constitute a function. And for what we have here, okay, so with the vertical line test, okay, you have solid points. Okay, so so you have in the region, so you have like at -1, +1, and +3. Okay, you have a couple of points, and say we have at -1, you already have the prevention of the graph display in 22 to be a function. So that is not the case of a function. And when we looked at number lines, okay, we've had like closed points and open circles. And let's say if I had open circles instead of closed points, okay, and I had this duplicated with open circles in place of closed points, I would not have any points with x values at -1, 1, 3, or -3, or even +5. And if I were to run a vertical line, okay, so you have like here, okay, you have open circles, but open circles are not included as portions of the graph. And so you would have, just like between the open circles, you have intersection at most one point with the vertical line. So if I had replaced the closed points with open circles, okay, then this would constitute a function. I just thought I would just throw that out. And now, okay, so 22 with the solid points, it prevents, okay, the full requirement passing the vertical line test. But again, if I had holes instead of solid points, then the segments would have constituted a function. Now, in the crossover, again, to looking at functional values and expressions, and we have four functions, okay, in the form of f of x, g of x, h of x, and k of x. And f of x, we have a quadratic function where we have this set equal to x squared plus 3x. And g of x we have as a reciprocal function where we have at 1 over x. And h of x is just a constant function where we have h of x is equal to 5, or that's another way of saying that y is equal to 5. And here we have that k of x is equal to the square root of x plus 1. Okay, now looking at the determination of function values, and say we have in number 46, we're looking at f of -5. Okay, and if we're looking for f of -5, so we are referencing f of x is equal to x squared plus 3x. So for the replacement of x with -5, okay, if I were to follow through, so we have for f of -5, that's going to be equal to the square of -5 plus 3 times -5. Okay, and the square of -5, okay, this will be positive 25. And we have 3 times -5, okay, that will be a -15. Okay, so again, we have 25 minus 15, and we have for this outcome, okay, we have -5, 10. Okay, and so if I had a graph of this quadratic function, -5, 10 will be a point on the graph. And now, looking at expressions, now going from a constant to just a variable expression, now I have f of a plus 4. So I'm changing the input from x to a plus 4. And if I follow through, so f the input is equal to the square of the input. And in this particular case, this is going to be the square of a plus 4. And we have plus 3 times the input. So that's going to be 3 times the quantity of a plus 4. And again, for what we have in following through, okay, so you have the square of a plus 4. So again, think of it like FOILing out a plus 4 times itself. And so we're going to have a squared. Outside product and inside product will be the same, with each at 4a. And 4 squared, okay, that is going to be 16. And looking at distributing 3 over the quantity of a plus 4, so that's going to be 3a plus 12. And looking at combining like terms together, okay, so you have a squared is the only second degree term in a that exists. And then for the first order a terms, we got 4a plus 4a is 8a. Then we have 8a plus 3a will make 11a. And for the constants, we have 16 plus 12, and so that will make 28. Okay. All right. So the input with the binomial a plus 4 is going to lead up to where the output is going to be a trinomial with a squared plus 11a plus 28. Now, working with the function g, okay, and we have constant inputs, and for number 39, okay, we have g of 3, and so we're operating in accordance with g of the input is equal to 1 over the input, and not much to do here. So replacing x with 3, we have that g of 3 is equal to the fraction 1/3. Now, for what we have in the case of 41, now we've got g of 1/3. And for this one, okay, so 1/3 is going to represent x. So in this case, we're not going to have 1 over 3, but 1 over 1/3. And so I have division by a fraction. And if I'm dividing by a fraction, it'll be the same as multiplying by the fraction's reciprocal. Okay, so I have 1 divided by 1/3 is the same as 1 times 3 over 1. And so the reciprocal of 1/3 becomes 3. Now, for what we have in the case of the function h, okay, so we have h of x is equal to 5. Okay, notice there is no variable output in the general case. So regardless of whatever we plug in for the input to represent x, okay, the output is going to be locked in at 5. So regardless of whether it is a constant, you have x represented by -7, and there's nothing to plug in for x this time around, so this will be locked in at 5. Same thing for h of x plus h. Still, the output is fixed at 5. Okay. So for 40 and 50, okay, we have the output at 5. Now, for what we have in the case of the function k, all right, so we have with k, again, we have the square root of the input plus 1. So you got k of x is equal to the square root of x plus 1. And replacing x with -5. And for this one, okay, so k of -5. Okay, it's going to be the square root of -5 plus 1. And -5 plus 1 is -4. And in this particular case, now we are not looking at the complex number system. We're just looking solely at the real number system. Okay, so for the square root of -4, you cannot have this in the real number system. And so in this particular case, we can say that the output is undefined or just simply no solution. Now, for x plus h, okay, so again, we're still dealing with k. And again, k of x is equal to the square root of x plus 1. And very little to do here. And once you replace x with x plus h, I don't think you can really do here is just say we have x plus h, followed by the addition of 1, okay, and there are no like terms to combine, so the square root of x plus h plus 1 winds up being the final output. All right, now, again, when we first looked at examples of functions, we started out with ordered pairs, and now, for what we have in the group, okay, from number 63 to 65. Okay, it says in 63 to determine f of 9. Okay, so f of 9, this is saying what the y value is whenever the input x is equal to 9. Okay, and so we have so where we have x to be 9, okay, the corresponding y value is going to be at 7. Okay, and for f of -1, this is going to be the y value whenever x is set to -1. So we have in this assortment x is at -1, corresponding y value becomes 6. And for f of 3, okay, we're looking at where x is 3 and what the corresponding y value is. So where x is 3, we have the corresponding y value is going to be at 4. Okay, so f of 9 is 7, f of negative 1 is 6, and f of 3 is equal to 4. Now, going back to domains and interval notation. All right, now we have in problem 100. Okay, so we have the radical functions involved, and for what we have in the case of problem 100, okay, and we have for these three parts, okay, so we have first of all, we're looking at the domain of y of t is equal to the square root of 16 minus t. And again, we're no longer looking at the complex number system, just what we have from the real number system to which we can apply these radical functions. Okay, so first of all, we had the square root of 16 minus t. Okay, and in the real number system, if you have an even root radical expression, okay, what is inside the radical cannot be negative. Okay, and because we have a square root, and with the square root being an even root, okay, so whatever we have inside the radical, okay, 16 minus t cannot be negative. Okay, now 16 minus t, it can be equal to 0 and it can be positive. So if I were to set things up along the lines of an inequality expression, okay, so if I had 16 minus t to be negative, it would be 16 minus t is less than 0. But it cannot be negative. Okay, now again, it can be 0 or positive. So the defining inequality in the setup, we're going to have that 16 minus t is greater than or equal to 0. And looking at solving for t and finding out what the inequality solution will be, as well as the determination of its domain, okay, we can isolate, first of all, we can isolate the variable term, which we have at the moment at negative t. Okay, so I can move the 16, and if I deduct 16 from both sides, so we have that negative t is greater than or equal to negative 16. And I'm looking at expressing the inequality in terms of not negative t, but positive t. And just some reminders. Okay, so if I go from a negative to a positive t, so I can either multiply or divide by negative 1. And the thing to remember is that if you multiply or divide by a negative, the direction of the inequality will change. And so we have in the change up, okay, so we got negative 1 times negative t is a positive t. And we'll have that t is less than or equal to 16. Okay, so for the value of immediate interest, okay, we have with 16, okay, and again, the nature of the inequality is t is less than or equal to 16. So with the equal part, 16 is going to be in the set, and we can indicate, say, in graphing by a closed point, and the other values in t will be less than 16. Okay, so you have moving continuously downward and going in the direction of negative infinity. So for what we have in the case of the function y of t we have for the domain. Okay, so you have going from negative infinity, approaching and including 16. Again, infinities are balanced, so we have a parenthesis to start out with. And since 16 is included, okay, that is going to be in the bracket. All right. Now, for what we have in the case of the function w of t, okay, in a sense, we're going in the other direction. Okay. And for this one, okay, we have the square root of t minus 16. And in a sense, okay, there's going to be a bit of history that will repeat, okay, because we have yet another direct even root radical expression, okay. And with the t and the 16 changing positions, now before we had that 16 minus t cannot be negative. Now we have that t minus 16 is that which is not allowed to be negative for this function w of t. And just like 16 minus t earlier, it can be 0 or positive. So that t minus 16 is greater than or equal to 0. And looking at isolating t, okay, so I can now add 16 to both sides. And doing so, I have positive t as opposed to negative t isolated. So we now have that t is greater than or equal to 16. Again, for this type of situation, if you're looking at just the domain, okay, graphing is not necessarily a must, but again, we're back in a situation where 16 is included thanks to the equal sign, and the rest of the values t will be greater than. So this time we have a ray that's going to go continuously out to the right and approach infinity. In this case, okay, so we're going to have for the domain, okay, now this time we have 16 as the lower limit, and it is included, so that is going to be in the bracket. And we have the upper limit to be positive infinity. Again, infinities remain in parentheses. All right, now for what we have in the case of part C, okay, we have z of t, and this is going to be the reciprocal of y of t. So z of t is equal to 1 over the square root of 16 minus t. And there'll be some level of repetition from the part A in number 100. Okay. First of all, you got a blend of a rational function and a radical function. Okay. And again, we have with the radical part, we got the square root. Okay, so you have square root of 16 minus t. This allows 16 minus t from being negative. Okay, but now the square root of 16 minus t, since it is now in the denominator, we have the added restriction that 16 minus t cannot be 0. All right, so 16 minus t. Okay, looking at the categories, it cannot be negative, it cannot be 0, and we have the only category that's going to be positive. Okay, so 16 minus t can only be positive. And for the defining inequality, notice before from part A, okay, I could have in direct terms, okay, the square root of 0, but I cannot have the square root of 0 in the denominator. Okay, so I had set up 16 minus t is greater than or equal to 0 in part A, but since 16 minus t can only be positive for the function z of t, we have the inequality set up whereupon 16 minus t is greater than 0. And so setting things up and solving for t, so now have taking 16 away from both sides. Okay, so we're back to where the isolated variable term is negative t. So negative t is greater than negative 16. And again, if I change the signs, either multiplying or dividing by a negative. Okay, so I have negative 1 times negative t, and the greater than changes over to less than. And so we have negative 1 times negative t is positive t, and t is less than negative 1 times negative 16, which is going to be 16. So I have t is less than 16. All right, and unlike parts A and B, 16 is not included. And for what we have in graphing, okay, so instead of a close point, we're going to have an open circle or a parenthesis. And again, for the values applied, you have those that will be less than 16. So we're going to have an array that will proceed to the left and head out continuously toward negative infinity. So for the function z of t, you will have for the domain, so I'm going from negative infinity, approaching but not including 16. Okay, and so we have an open interval with parentheses that will encapsulate negative infinity and positive 16. All right. So you have for 100, you have variations upon which we have the variable expression to be involving a square root radical. Now, for what we have in the case of number 104, part C, okay, now we have with our function t of x, okay, so you have t of x. Okay, so you have x plus 1 all over x squared minus 4x minus 12. Okay, so there's no even root radical in this one. Okay, but we do have a rational function, and again, for rational functions or fractions, okay, the denominator cannot be 0. Okay, and so we have the restriction that x squared minus 4x minus 12 cannot equal 0. Okay, and looking at pinpointing the value or the values, okay, that x cannot be. So I can just take an approach with the zero product property, but with the expression and the factors not equal to 0. So from x squared, this will factor out to x and factors of -12, whose sum or difference will be -4. This will stress that more weight will be given to the subtracting than to the adding. Okay, so we have on the plus side, we have only 2, and on the side of subtraction, okay, we have taking away 6. All right, and this time we have with our distinct factors. Again, this time setting up where the factors cannot be 0. Okay, so for the first of these, if x plus 2 cannot equal 0, well, it's going to turn out that x cannot be equal to -2. And if we have also the x minus 6 cannot equal 0, we're going to have the x cannot be equal to 6. Okay, so we have 2 exclusions from the domain, and those exclusions being those values that will cause the denominator to be 0. Okay, so we have so we got -2 is left out, and also +6 is excluded. And just looking at it from a graphing standpoint, so -2 is left out, 6 is left out, and all the other numbers in the real number system will be in the domain. So just looking at what we have here, so everything less than -2 is in the mix. And everything greater than -2 and less than 6 is also in the mix. And then we have in the upper realm, okay, we have those values of x greater than 6 in the domain as well. And so we're going to have for the domain, okay, so you have at the lower end, you have those values of x less than -2. Okay, so you have parentheses throughout. Now, we're bypassing -2, and then for the middle section, yeah, those values greater than -2 and less than 6, where -2 is less than x is less than 6. And for the interval notation, we have parentheses around -2 and 6. And then we have for those values of x greater than 6, again, we're bypassing 6 just as we did -2 a moment ago. And we go ahead and, so again, we're bypassing not 2 but -2. Okay, and then we have for the final strip, okay, we have the ray going out to the right, and so this represents the values of x greater than 6. And so throughout, okay, you have these 3 subinterval sections, and with problems like these, the more itemized exclusions there are, the more of these subintervals you're going to end up witnessing. Okay, and now, and again, just domain is a topic that is going to be occurring time and again. And now, for what we have regarding functions, we're just going to kind of take a bit of a break from the individual terms like domain and the vertical line test and all that, and we're going to kind of cross over to equations. And for what we have in the next item, okay, so we're going to have what we refer to as linear equations in 2 variables. and linear equations. Those will be the items we will be working with the XY coordinate system, and we have stuff like the slope-intercept equation, the point-slope formula, and just foundation to linear equations in two variables, especially with the XY coordinate system. You have one of the bedrocks will be the slope of a line. And in this one case, so we have, by definition case, you have the slope of a line. Now I'm going to add in this adjective. See, I like the slope of a non-vertical line. That runs through 2 points. Again, in the XY coordinate system, we have in points, you have X to come before Y. So we'll say we have a first point. We'll designate this with the subscripts. We have X01, Y01. And the second point, we'll just say we have X of 2 and Y of 2. And we have for the slope. Now there are various letters that can represent slope, but I think in a lot of the contemporary math textbooks, you will have the slope to be represented by the letter M. And the slope is going to be the rate of vertical change with respect to horizontal change. And the most common display is where we have utilizing the coordinates. We say we have Y of 2 minus Y of 1 all over X of 2 minus X of 1 and again, you're just looking at the amount of vertical change with respect to the amount of horizontal change. And for X of 2 minus X of 1, to avoid having a zero-valued denominator, X of 1 and X of 2 cannot be equal to each other. Now, if they were to, if X of 1 is equal to X of 2, then what would arise as a consequence is that the difference between same values is going to be 0. So you have a 0 denominator. And you have that the slope is undefined. And if we have that the slope is undefined, this is going to mean that the line is vertical. All right. So again, just kind of stressing, non-vertical. Okay, so for a defined slope, the line must be non-vertical. But if you have a vertical line, there's no change in x. It had the same x, but your motion is going to be straight up and down, and your slope is undefined since you would have a zero value denominator. Okay, since we have no change in x. All right. Now, where we do have the slope to be defined, and say we're looking for the slope of a line that's going to run through so you have two particular ordered pairs. Let's say we have -1, -4, and 3, 6. Okay, so just setting things up for what we have in terms of the formula, and also just kind of I'll provide a bit of a visual, kind of a rough sketch. Okay, so you have the x-axis and the y-axis. So we have 3, 6, and -1, -4. And the line that's going through both of these points. Okay, and again, I'm not drawing this perfectly to scale. Okay, but with what we have in the setup, okay, so you got 1, 4 and 3, 6. Again, we have with our slope formula, you have y of 2 minus y of 1 all over x of 2 minus x of 1. So you want to identify just what the x and y terms will be. Okay, so you got 1, 4 and 3, 6. Now, it doesn't matter which one we have as the first set, but since not 1, 4, but -1, -4, since this is provided first, say we have x1 is equal to -1, and y1 is equal to -4. And since 3, 6 is given subsequently, and again, all ordered pairs are the form xy. So say we have x of 2 is equal to 3, and y of 2 is equal to 6. Okay, so if we go at this route, have -1, -4 as the first point, 3, 6 as the second, and we have substituting accordingly. Okay, so for y of 2 minus y of 1, we have 6 minus -4, and for x of 2 minus x of 1, so we're going to have 3 minus -1. Again, subtracting a negative reverts to addition of the positive. So we have 6 plus 4 at the top and 3 plus 1 on the bottom. So right now we have, for the vertical change, we got 6 plus 4 is 10. And for the collective horizontal change, we have 3 plus 1 is 4. And we have for the slope, okay, we have 10/4. And that fraction is reducible to 5/2. And just in the cyclical pattern, okay, so you got positive slope. So you can say that we have a cycle of moving up 5 units while shifting over to the right 2 units. And you can create a little bit of a staircase pattern. Okay, say like from -1, -4. Okay, and that should be straight up. So I'm kind of okay, so I'm going to go up 5 units and shift over 2 units. Okay, so you have a bit of a triangular formation along here, so you kind of like have a cycle of going up 5 units and shifting over to the right 2 units. Okay, and if I start at -1, -4, so your y value goes from -4 plus 5 to y is equal to 1, and then shifting over 2 units, I'm going from -1 to +1. So you have like an intermediate point, which would be at 1, 1. And if I go up 5 units, I'm going from y is equal to 1 to y is equal to 6. And shifting over to the right 2 units, I'm going from x equals 1 to x is equal to 3. Okay, so you have like an up 5, right 2. And to stay on the line, you're going to maintain that particular cycle. Okay, so for this line, okay, we come out with the slope at 5/2. And now for what we have regarding the equations of given lines. And the first of these, we'll have what is regarded as the point slope form of a linear equation. And in short, that is often referred to as the point slope equation. Okay, so you have like the point slope equation of a line. With slope m and that's going to run through a point. So we have x1, y1. Okay, so in this particular case, the point slope equation is going to be in the form of where we have y minus y01 is equal to the slope m times the quantity of x minus x of 1. Okay, so this layout is going to be the point slope form of a linear equation. Now, if you notice, okay, in ordered pairs, we say x before we do y. But in this arrangement for the point slope formula or equation, you got your y's out at the front. And from the point slope equation, okay, we have isolating y. Will lead to the formation of what is formally called the slope-intercept form of a linear equation. Okay, so for the y jutted out at the front, okay, that was going to be isolated. And once you put together like the coordinates along with the quantified expression, okay, multiplying the slope, okay, once the parentheses are removed and you have y isolated, again, you have for the slope-intercept equation, again, we had that y is equal to mx plus b. And for what we have in the case of the variables, again, m is still the slope. So that value is fixed. And the intercept part, okay, of the slope-intercept form, this is be referencing the y-axis, okay. And so that b part gives me indicating what the y-intercept will be. And this intercept can be identified in at least 2 different ways, okay. Y-intercept, I know like in Alex, he likes to express it in terms like y is equal to b. Whereas in the case of the textbook, and I normally put this in terms of the ordered pair, where when x is equal to 0, y is equal to b. So y-intercept, you can say that y is equal to b, or as an ordered pair, we have 0b. Okay, and let's say that if we're looking at determining both types of equations. And say we have, just for example, see we have, first of all, to determine a point slope equation, and subsequently the slope intercept equation. Let's see, we have given, first of all, okay, I have the slope provided. Okay, so we have that m is equal to 5. And we'll say that we have x01, y01. Is equal to -1, -2. Okay, this is what we have provided. So the slope is given, and the point through which the line passes, okay, we have provided at -1, -2. Now for setting up what we have in point slope equation terms, okay, so this is our algorithm. And again, just like when we looked at determination of slope, you want to get, okay, the coordinates identified. Okay, so you just want the proper substitution. So we have with -1, again, x1 is equal to -1, and with -2 as the second coordinate. And since the second coordinate is in terms of y, you had the y01 is equal to -2. Okay, so we got the slope m at 5, x01 is -1, and y01 is at -2, and substituting accordingly. So for y minus y01, we have y minus -2, and we have the slope m, which we have at 5. And for the quantity of x minus x01, we have x minus -1. Okay, so this is what I have so far from directly substituting these values and then just undoing the presence of subtractions of negatives. Y minus -2 becomes transformed to y plus 2. And we have is equal to 5 times the quantity of x, and what's going to be plus 1. Okay, and for what we have at this step, okay, this is going to be the point slope equation that corresponds. Okay. Now if I'm looking for the slope intercept equation, okay, so I'm going to take care of the parentheses. So say we have y plus 2 is equal to 5x plus 5. And setting the stage whereupon I can isolate y. Upon taking 2 away from both sides, we had that y is equal to 5x plus 3. and this will be the slope-intercept equation. Again, so you got your m at 5. And if I were to identify the y-intercept, okay, so you have the 3 that follows. Okay, you have, this will signal that the y-intercept you can write as y is equal to 3. And again, we have as an ordered pair. And this will come out to 0, 3. Okay, so you have, for these equations, okay, so again, you have y plus 2 is equal to 5 times the quantity of x plus 1. Again, that's the point-slope equation. And for the slope-intercept equation, that is whenever you have y isolated and have the equation in the form of y is equal to mx plus b. Okay, and just I think I might have this up and just providing a visual. So y is equal to mx plus b. So you have y is equal to 5x plus 3. And again, we had slope at 5. And the given point we had at -1, -2. And we said that the y-intercept is 0, 3. So just looking at the visual layout. Okay, so you got y is equal to 5x plus 3. And you have various inputs for x. Okay, so you have among the ordered pairs, you have -2, -7. And again, we had the given point, -1, -2. And again, there's that y-intercept at 0, 3. And other points, if I stay on the line, maintain the slope of 5. So you have 1, 8 and 2, 13 among infinitely many other points that would belong to the line represented by the equation y is equal to 5x plus 3. Now, let's say that if we have a case here whereupon we have, let's say we had that the slope is negative. Say have the slope is equal to -4. And we'll say that we have the point through which the line will pass will be 2, 6. And again, just laying the groundwork for the point-slope equation as well as the slope-intercept equation. Okay, so I got the slope at -4. And again, with the order pair 2, 6, I guess I have x of 1 is equal to 2. And 6 will be the y of 1. And it's very easy to get things crisscross. Again, we say x before we do y, but the formula has y before the x. So be careful with what you put in for the x of 1 and y of 1. So y minus y of 1 is going to be y minus 6. And for the slope m, again, that is -4. And for x minus x of 1, so we have x minus 2. And guess what? We don't have any double negatives to undo, so we have with this layout. So this is our point-slope equation, and looking at setting things up to determining what we're going to have with the slope-intercept equation. Okay, so I can distribute -4 over the quantity of x minus 2. So we have y minus 6 is equal to -4x plus 8. And once again, isolating y. So I can do this upon adding 6 to both ends. Okay, and so we have y is equal to negative 4x. And you have plus 8 plus 6. And so this will come out to 14. And again, so this is going to be the slope-intercept equation. And again, so you had the slope m. Just kind of regurgitating. Okay, so you had the slope m is equal to negative 4. And the 14 will be the indicator of the y-intercept. So for the y-intercept, say you have y is equal to 14. Again, in ordered paired terms, we have 0, 14. Okay, so for what we have with this equation, okay, so we now have in the visual layout, now again the slope is negative 4, and if you read the graph in order from left to right, okay, we have for a straight line, again, whenever the slope is positive, like what we had immediately earlier, okay, we have motion upward as the graph proceeds from left to right, but whenever the slope is negative, okay, we have downward motion. And again, so we have with y is equal to negative 4x plus 14, and sample values x we can plug in. So we got negative 222, negative 118, and here we have our y-intercept 0, 14. You also have 110, and again we worked with the given x and y values at 2 and 6. Okay, and so that will be the dynamic that will be played out for this particular equation. Now, okay, so for these two cases, okay, I've had the slope provided, but let's say that instead of having the slope given, we'll say that the line is going to run through 2 points. Okay, so you have 0, 6 and 2, 12. Okay. All right, so we don't have the slope given, okay, but if you recall, okay, from the start when we looked at the determination of slope, okay, we had used 2 specific points, and here kind of going back to square one, so we're working with 0, 6 and 2, 12, so you're kind of going back to the x1, y of 1, x of 2, y of 2 formatting. Again, so you have for slope, again, so you have the ratio change in y with respect to the change in x. Okay, so looking at the determination of slope, and I know that like over the years, okay, some will like to go ahead and be working with the slope before they clearly define, okay, just what is going to represent the subscripted x and y terms. Okay, so we have, remember, all ordered pairs are of the form xy, and okay, we want to identify, okay, just what the x of 1, y of 1, x of 2, y of 2 expressions will be, okay, and it doesn't matter which of these 2 points we'll have as the first, but we'll say that since 0, 6 comes at the front, we'll say 0 be the first x, and 6 will be the first y. And with 212 given subsequently, let's say that 2 is going to be the second x, and that 12 will be the second y. Okay, and with these values specified, so y of 2, we have at 12, subtracting y of 1, so y of 1 we have at 6, for x of 2 minus x of 1, so x of 2 we have at 2, subtracting x of 1 we have at 0, and we have 12 minus 6 is 6, 2 minus 0 is 2, and so for the slope we have a 3-to-1 ratio, so that's like moving up 3 units while shifting over to the right 1 unit. And so we have that the slope is equal to 3. Okay, so we got the slope m. Okay, now for the x of 1, y of 1, you can actually choose either of these two ordered pairs. So you can choose 0, 6 or 2, 12. For x of 1, y of 1. Say in the point slope setup, and again, it does not matter which one you use. Okay, if you choose 212, that works, but we'll go with 0, 6 on this one. Okay, so just kind of hitting the reset button. Okay, so you have for 0, 6. So you have x1 is 0, and y1 is at 6. But if I had let x1 be 2 and y1 be equal to 12, it will also work. But so setting the stage, through the point slope setup, again, just doing a little bit of color coding. Okay, so you got for y minus y of 1. Okay, so we have y minus 6. And we have is equal to the slope m, which we have at 3. We have times the quantity of x minus x of 1. Okay, so the x of 1 we have at 0. And choosing this point to work with. This is one of the point slope equations. Now I'll just mention this too on the side. I didn't select 212. But the other one would have been, let's see, y minus 12 is equal to 3 times the quantity of x minus 2. That would have been the other possibility. Okay, but just with what we have now, so we got y minus 6 is equal to, and x minus 0 is x, so I got y minus 6 is equal to 3x. And adding 6 to both sides. And we're going to have our slope-intercept equation, okay, whereupon we're going to have that y is equal to 3x plus 6. Okay, so this would be our slope-intercept equation. And again, the slope m is equal to 3. And for the y-intercept, okay, so the b value comes out to 6. So y is equal to 6. And in ordered pair terms, okay, we'll come out to 0, 6. All right. And just for what we have in the visual layout. Okay, so for y is equal to 3x plus 6, again, we had, if you notice, okay, we have in the table, okay, we have the coordinates of concern we started working with. You got 0, 6, which is our intercept, and this is one of our given points. The other given point we have at 2, 12, which is also on the line. And again, other ordered pairs included will be including negative 2, 0, the x-intercept, along with negative 1, 3, 0, 6, 1, 9, as well as 2, 12. Okay, and tell you what, just in the case of looking at slope as well as determining the slope-intercept equation, just for the next few moments. Okay. Okay. First of all, okay, say we determine the slope of the line. That's going to pass through 2 points. And we'll say that we have negative 1, negative 7, and say we have 6, negative 5. So in this one, just determine the slope. And then we'll have, secondly, okay, the slope-intercept equation. And we'll say we have the slope is equal to negative 7. And we'll say we have the ordered pair through which the line passes. We'll say is going to consist of let's say we have 3, negative 4. Okay, just for these two problems. Okay, first of all, we're looking just for the slope of the line that's going to pass through these 2 points. Okay, so you have negative 1, negative 7, as well as 6, negative 5. And, okay, so we got it in the setup. So for negative 1, negative 7, and 6, negative 5. Now we can have x01, y01 to apply to either of these 2 points. We'll just let -1, -7 be the first set of x and y values, and have 6, -5 to be the second set. All right, so we have for the slope m, okay, we have y of 2 minus y of 1. All over x of 2 minus x of 1. And again, substituting, okay, so we have with y of 2 at -5. Okay, so we have -5 minus, okay, y of 1 we have at -7. Now for x of 2 minus x of 1, x of 2 we have at 6. We got minus x of 1, so we have minus -1. So we're in the terrain of subtracting negatives. Okay, so we have -5 plus 7 in the numerator, and in the denominator we have 6 plus 1. And we have -5 plus 7 is going to be a positive 2. And 6 plus 1 is 7. So we have for the slope, okay, this is going to be a non-integer positive value where we have 2/7. Okay, so we have kind of a flatter line in comparison to the lines we have dealt with. Okay, if you were to graph, okay, so you look at a cyclical pattern whereupon you have like going up 2 units and shifting over to the right 7 units. All right, now for what we have in looking for the slope-intercept form of a linear equation, with what we have provided. Okay, so we have the slope at -7, and we have the given ordered pair with 3, -4. Okay, so we have x of 1 is at 3. We have y1 at -4. And again, we have in our toolbox, okay, we have the slope at -7. Okay, so through the point slope pathway to arriving at the slope-intercept equation, and looking at substituting, okay, so you got y minus y of 1. So you have y minus -4 is equal to the slope m, and we have at -7. We have times the quantity of x minus x of 1, so we have x minus 3. And again, we have with the double negative on the left, in case we have y plus 4. And I'll distribute on the right in the next step. Okay, now for what we have at this juncture, okay, so again, this is going to be the point slope equation. Now we're looking for the slope-intercept equation, okay? So I'm going to isolate y. And for what we have in following through, so we've got y plus 4 to the right, okay, distributing -7 over the quantity of x minus 3. Okay, I'm going to have -7x plus 21 and just getting y by itself. Upon taking 4 away from both sides, so we'll come out to y is equal to -7x, and 21 minus 4 comes out to positive 17. Okay, and so that would be the slope-intercept equation, okay, for this particular line. Okay, and again, so you have like the slope is at -7, your y-intercept would be located at y is equal to 17, or as an ordered pair at 0, 17. Okay, and just without even graphing, you can just sort of check the consistency. So we still have the slope at -7, and to see if x01, y01 is a point on the graph represented by y is equal to -7x plus 17. So you have, so working with 3 and -4, so we have -4 in place of y. So the left-hand side is -4, and I want the right-hand side to be as well. So y is at -4, and with x at 3, right-hand side we have -7 times 3 is -21, and -21 plus 17 also comes out to -4. -4 is equal to -4, and so we got everything to check out. So that is going to be, once again, the slope-intercept equation with y is equal to -7x plus 17.